Alex Esselin Botelho is from Cadence Design Systems, where he is a senior principal application engineer. He's going to be talking about formal verification adoption made easy. He joined Jasper over 10 years ago, initially part of the quality assurance team in the R&D organization, and later as the quality assurance manager. He moved to Cambridge in 2017 as an application engineer supporting formal over Northern and Nordic EU countries. So I'm going to go straight over to Alex. Over to you. Thanks, Alex.
Thank you. All right, so as Michael was saying, I will talk about, in the context of formal verification adoption made easy, I will talk about first about the JasperGold apps that we have in our catalog, and then I will give you an idea of methodology about design RTL bring up, kind of following what Nir was experiencing here when he was writing his own properties. So this is the agenda for today. I will give you again an overview of the apps, and then expanding on the methodology discussion, I will try to ask the question, when is your design ready to hand off to verification? I will talk about the challenges of RTL design bring up, and I will also talk about this methodology. I will end up with a summary and the Q&A. All right, so let's start with the verification throughput and JasperGold apps, just to situate everyone here. Of course, all of the speakers today are talking about formal, and in Cadence's offer, formal verification is one of the verification engines together with simulation, emulation, and prototyping. We are talking here about formal, about JasperGold. Let me just turn on my pointer here. And as most of you might be aware, right, the idea is that the tool will mathematically prove properties, as Nir was describing. And we do, the tool does automatically exercise all input combinations. And this is key for understanding the methodology of what we described today. One historical limitation of formal is the scalability, right, beyond block IP level. But model checking has been progressing on scalability and performance a lot over the last 10 years. And at least from our perspective, from our market perspective, we do think that it's a mainstream technology and an extension verification tool for your teams. In Cadence, we have a product called JasperGold. It's a platform which contains many apps, which I will not describe here, but the idea here is that we are trying to verify specific behaviors of the design through the usage of those apps. I will focus though on formal property verification app, which is the more generic one, and on the SuperLint app, which is our link checker. With that, we also have a feature in Jasper called Visualize, and this is our waveform viewer. So I would say it's a more intelligent waveform viewer, as it contains many formal enabled features for you to understand what's going on the design. And of course, this is all supported by our broad portfolio of formal engines. It's supported by the assertion-based IPs that I will talk about also today. And as all our other tools, it's programmable via TICO, and it's scalable as well. So the summary here on the slide is just to show that there's our offering has a breadth of solutions right across the entire SoC development progress, from RTL development to SoC integration. But today I will talk specifically about design handoff and verification. So let's start with that. The question I want to ask here is, when is your design ready to hand off to verification, right? When we think about this question, we can enumerate several items as a task list. For example, the first one is if we could start by linting, right? Seeing if all the lint checks are passing based on a predetermined baseline. There are no basic structural checks. In JasperGold's case, this can be done with the SuperLint app. We want to make sure that the initialization looks correct. So we are not expecting any uninitialized flops, for example. So as we come out of reset, we are not expecting any untied flops to drive axis. We also want to make sure that either the RTL is fully reachable, but if it's not reachable, that we understand the fact that it's not reachable, right? So if it's, in this case, it's waived, so we don't have any surprises later with the system level coverage. We also want to make sure that interfaces are clean, there are no protocol violations, and that our DUT communicates correctly with other blocks. We also need to confirm that configuration bus, the configurations that we set through the bus for DUT are covered, all the modes are covered. And this is key on the methodology talk I will give today. We also want to make sure that all the critical good behaviors can be covered. Another item, there are no failing generic functional behaviors. And when I say generic, I'm talking about checks which are easy for the tool to generate automatically. For example, overflow checks for counters or deadlock checks for FSMs and so on and so forth. Two more items. The next one, if I have waivers, if I've looked through those things and there are items which I need to waive out, and that those waivers can be saved and reused later. And finally, that all of the interface properties that I've written for a block can be exported. So then it can be checked at the system level. So when we are talking about this design bring up, there are many challenges that a designer or even a verification engineer will face. And therefore, I will compare the traditional bring up using simulation against a formal verification bring up. So let's start with the challenge number one, right, which is missing pieces. Let me just move this window here to the side, sorry. Yeah. So in traditional bring up, there are often modules that are not yet compiled, and this is especially true when they are still in development, right? So it's not always the case where you have a full RTL or a full DUT. Modeling those missing blocks can take a lot of time, and it's usually a prone to error situation. The module is often thrown away, and it's not really verified anyways, which actually brings, if you have it modeled incorrectly previously, you can be testing your design under incorrect assumptions, which will then never be caught in the future. When we compare this to a formal bring up, right? Usually the missing box modules can be black boxed by default. Those black box outputs will allow all possible output behaviors, even if they're not really moduled. And but you can also constrain a bit this behavior using assumptions. Even if it in a more abstract way, for example, if it's the output of a data register, which you know that cannot go above a certain value, you can just write that constraint easily with a simple SVA expression. And the good part here about the missing pieces is that once you have the implemented block, which was missing before, black box, you can then reuse the assumptions you wrote on the second item as asserts, right? So you can make sure that the assumptions are then verifying the correct behavior that you've written. Second challenge here for bring up stimulus. In traditional bring up, people spend a lot of time trying to inject the correct stimulus for each test. It is time consuming to generate the stimulus, especially if it has to be protocol compliant. And stimulus used at the block level is never really double checked right at the system level. With formal bring up, the approach here is a bit different. So usually in formal verification tools, you can choose the target behavior you want to see, and formal then creates the stimulus for you. In this case here, this guy is the target is that he wants to see that if this state equals to read, and he wants to see and acknowledge. And in JasperGold, you can even navigate through the source code browser and ask those behaviors to be shown in a waveform quickly just by browsing the source code browser and asking the tool to show it to you. you can leverage protocol compliant constraints and checks, which might be available from previous blocks, right? Blocks that were interfacing with your DUT, or IPs that can take off the shelf, like the Cadence Session ABVIPs, Cadence ABVIPs. For example, you can get AXI4 ABVIP, which will already contain not only the assumptions to behave as an ABVIP master, for example, but the assertions to test that your DUT, for example, implements an AXI slave, for example. And finally, you can actually use those constraints, again, the ones that you've written on the interface, to on a higher level to verify that the higher level is then implemented according to spec. A third bring up challenge here is checkers. It's usually the designers are presented with this daunting task of developing the checkers for important behaviors. Usually you have to think carefully about what to check and when to check it, and it will often require, for example, implementing scoreboards. Each of the checks might require a specific set of stimuli, which could be difficult to generate again. And the checkers you create usually provide little value to other RTL developers of the verification team. Whereas in formal verification, again, since it's a targeted technology, you either write what you want to see or you write what you never want to see. You don't really have to worry about the stimulus. The tool will generate the stimulus for you, and therefore you can switch your focus as a designer, which is trying to bring up this on formal, or as a verification engineer who's trying to bring your setup on formal, to a more targeted approach, a focus on the end behavior. You can, from a waveform, which you've seen in the tool, using JasperGold, you can capture that behavior into a property by interfacing with the visualizer. And on top of that, the tool also generates a lot of generic behavior checks, for example, arithmetic overflow, X assignments, deadlocks, which you can also then export to an SVA property. Those SVA properties can then be reused, for example, in simulation. A fourth challenge is that code in Unreachable, and again, I will use Neo's presentation, right, with the Unreachables as an example. In traditional bring up, you might be trying to simulate behaviors which we will never really get because they are unreachable. And for the unreachable behaviors that you are expecting, usually there is no way to confirm that with simulation. Since formal is a mathematical tool, it approaches it by proving that the behavior is reachable or not. You can ask the tool to demonstrate a cover for you. And if it says it's impossible, then you already know that, for example, that it's what you would expect, for example, a feature that was not implemented yet. And this can be done either with the SuperLint app, which I will talk about a lot here today, or the coverage app, for example. Challenge number 5, so poor visibility at the system level. Bringing those properties up to a higher hierarchies of the design. So in traditional bring up, once you send the RTL over the wall, right, you as a designer, to the verification team, are you really sure that they are exercising the things that you are concerned about? So bugs can often escape at the system level tests if you're not really testing them. For bring up, again, so the behaviors that you write, that you've saw and visualize when you're doing the bring up activity, you can then capture in SVA properties, right? So answering in this case here, the quote, here are the things that you should be exercising in system level simulation, and those properties are then compiled in sim and then tested exactly in simulation. Challenge number 6, pinpointing the root cause. And in traditional bring up, it can be kind of hard to explain exactly what's going up, and that is because in general, traces are much longer than formal verification traces. When a failure happens at the system level, it's hard to root cause it, right? Find which blocks led to the failure, how is the failure modeled inside the block, for example. Whereas in formal, during the bring up, the tool, most often than not, usually it finds the shortest possible waveform that shows the behavior, which minimizes the debug time. And in our tool specifically, there are many features for you to understand what's happening. For example, there's the Y analysis where you can double-click signals and understand where the assignments came from, annotated in the source code browser. Or, for example, the quiet trace technology, where if you have a very noisy setup, you might ask the tool to generate a new trace for you, which is a bit more clean. It still shows the violation, but in a more clean, more easy to understand waveform. And finally, again, all of those properties can then be exported as SVA properties that can then run in your system level simulations, for example, to pinpoint exactly where the problem is. So there's no more waste of time debugging this backwards from the system outputs. All right, so let's talk about this methodology that I will describe here today for you. But before we do this, let me just take a quick look at the anatomy of various RTL bugs that we can find, right? If you were to classify all of the RTL bugs that you have ever seen, then you might consider a table like this where you can categorize them based on different checks: detectable by structural checks, visible when exercising expected behavior, would violate generic behavior checks, would violate protocol at external ports, and would it violate functional specific assertions. And if we think about the kinds of bugs that we can find on the RTL, you can categorize them by low to high. So in this example here, right, unconnected internal signals are very easy to find by looking at store checks, for example. Out-of-box indexing can easily be detected by generic behavioral checks. If you have indexing in your design, that you can just generate those automatically for you, for example, using the Throughput tab. Corner case protocol violations, it usually requires a product like the ABVIPs, right, where a full protocol is implemented, and you can then find those violations with the properties on the external ports of your protocol. And you can also find by looking at specific assertions. When we look at those, right, there is a good chance that we can expose many of the bugs that we are looking here by just wiggling the design, just really exercising expected behavior, which is this column that's highlighted here. And of course, there isn't a clear method, the best method of detecting every type of bug. A good methodology will require diversity in the types of analysis that you do. But the takeaway here is that for all of those bugs that we are listing here, it is interesting to actually look at the expected behaviors, right? So let me talk about this methodology then. So we can start our bring up by compiling the design and performing basic structure inspection, right? Our goal here is to look at the structural characteristics of the design, for example, seeing how the design behaves after reset. We can then move to linting and superlint that code checks, right? Where you can check if your design is compliant with code style, coding guidelines, or checking about the reachability of the designs. And the next step is actually writing properties with interesting behaviors. Again, those are not complete checks. Those are interesting behaviors that you as a designer or verification engineer would like to see. A FIFO being full, maybe a transaction finishing happening, and so on and so forth. You let tool generate those stimuli for you, and the tool can either say that the behavior is unreachable, therefore there is a possible bug, or there is actually a plot. There is actually a plot which shows that behavior. And with that plot, you can then capture that property, which is the important part here. So you pin exactly the behavior you would like to see as a preparation for your formal bring up, as a formal setup. You can ask the question, are more behaviors to explore? And if the answer is yes, you just iterate over this process over and over again. Once we've done with all of this exploration process, we can then move to debugging the interface failures, for example, debugging more generic behaviors with Superlint, for example, the overflow checks or the out-of-bounds access. We can start looking at the design-specific behaviors, which are the more complex assertions that were written. And again, every time you see a cover, a waveform of what you're trying to see, of you're trying to prove, right, what you were seeing, you can capture that into a property. And finally, exporting that to SVA. I don't have many minutes, so let me just try to wrap. When you think about, if you take a step back, and if we take a step back and look this methodology, right, we not only have addressed all of the typical challenges with the design bring up, but we've also completed all of the steps required to hand off that setup to our verification engineers, for example. So to summarize, designers are faced with many challenges when trying to bring up their designs, but using a solid methodology combined with cutting-edge formal capabilities, they can perform design bring up and address each of those challenges. By going through each step of the flow, the designers can be confident that they have addressed each criteria required for handling their RTL over to the verification team. And the design bring up methodology can replace unit level simulation while also providing team-friendly capabilities through the use of portable properties. I will just skip this slide quickly. This is the end of my presentation. Do you have any questions? If I have the time.
Thanks, Alex. Yeah, we're nearly out of time, but maybe just time for this one quick question, and we'll send the rest of them by email. So the first question was, can formal tool get 100% code coverage at block or module level?
Yes, it can. It can, but it is going to depend on the complexity of the block, right? Ideally, you could, all the solvers would run, they could run for infinity, but usually at module level, that's not what we see. We can get 100% code coverage. Code coverage, reachability, very fast.
Okay. Okay. Unfortunately, we'll send the rest of the questions by, on email to you, Alex, because we're out of time. So thank you very much for your presentation. Very helpful as well, and I like the 10 challenges that you went through. So thank you very much.
Thank you.